The diagram shows a circular clock face with the hands not shown. The square part of the clock face is glass so that the mechanism is visible. Two circular cogs, H and K, which touch externally are shown. The point C is the center of the clock face. The point D is the center of the larger cog H, and the point E is the center of the smaller cog K. So in suitable coordinates we are given the equation of the circle H, and we want to get the radius and coordinates of the center. Now we saw before that the general equation of a circle is given by this here, where HK is the center and the radius is the square root of h squared plus k squared minus c. Now you may be using letters minus g minus f instead of h and k. Okay, so this may be minus g comma minus f, and over here we'll have root minus g squared, or just g squared, plus f squared minus c. Now if you change it to that notation, instead of minus 2hx you'll have plus 2gx, instead of minus 2ky you'll have plus 2fy. But as I explained before, we don't need to use this minus g minus f notation. It's actually quite confusing, so I'll just work with h comma k. So we see that minus 2h, the coefficient of x, is equal to 4. So h is minus 2, and the coefficient of y is 6. Minus 2k is 6, so k is minus 3. So basically we halve these quantities and change the signs. Now we can get the radius, so we plug minus 2 and minus 3 in for h and k. C is the constant term in the equation. You can see that c is minus 19, so we have minus 19 or plus 19 here. We get root 32. If you want to, you can write this by factorizing 32. So we get root 16 by root 2, or 4 root 2. The point E has the coordinates 3, 2, and we want to get the radius of circle K. We've seen before when circles touch externally, that is, they touch at one point, the distance between the centers of the circles is the sum of the radii of the two circles. To get the distance between the centers of the two circles, we use Pythagoras' theorem, of course, or you can simply plug the coordinates of the 2 points D and D into a formula. I'll just work it out from our right angle triangle here. If we look at the difference of the y values, we have 2 minus minus 3, that's 5. And as for the difference of the x values, we have 3 minus minus 3, 6. So the hypotenuse is the square root of the sum of the squares of the two short sides. If you work that out, you get root 50. If you factorize 50 as 25 by 2, you can write this as root 25 by root 2, or 5 root 2. One good reason for writing it in surd form is that to find the radius of circle K, we can just take this surd and subtract 4 root 2. Both surds involve root 2, it's easy to subtract them. So 5 root 2 minus 4 root 2 is 1 root 2. Next we're going to get the distance of the point minus 2 comma 2 to the line DE. DE is the line joining the centers. Now the distance that we want, of course, is the shortest distance of the point to this line, which is the perpendicular distance. So we saw before how to do that using a formula. However, I'm going to do it in two ways. So one way is to consider this triangle here. So we're looking at the big triangle. Well, that's actually a right angle triangle, because we see the point D is directly below the point C. You can see that the x coordinates are the same. And the point 3, 2 is directly to the right of the point minus 2, 2, because the y coordinates are the same. Let's get the area of this right angle triangle. So we need distance from here to here. Well, that's easy. That's the distance of 2 to minus 3. Well, that's 5. 2 minus minus 3 is 5. And what about the distance between C and E? Well, we just subtract the x values. That's 3 minus minus 2, or 3 plus 2, which is 5. So we see that these two sides are the same, so they're the sides of a square. Well, I'm going to redraw this. Here I've drawn in the diagonal of this square. Now we know that the diagonals of a parallelogram bisect each other. A square is a parallelogram. So in particular, this diagonal here is bisected into two equal parts. Also, the diagonals of a square are at right angles to each other. Now we could show that in a number of different ways, but a quick way that we could show it is to imagine rotating our square about this center point by an angle of 90 degrees. Well, if we do that for a square, the square will just land on itself. It will look exactly the same as it did before. So in particular, this diagonal here will land on top of this second diagonal. So that also tells us that since this diagonal is bisected, well, it's true for any parallelogram, but even more strongly, these two are the same as these two. So all four of these lengths are the same. So straight away we can see that the distance d that we're looking for, the perpendicular distance of C to the line DE, is half the length of the line DE. So D is half of the line segment DE. The translation which maps the midpoint of the line DE to the point C maps the circle K to the circle J. Find the equation of the circle J. So we just look back at the picture to get the coordinates of D and E. We get the midpoints of those coordinates, okay? So we just get the mean of the x values and the mean of the y values of the points D and E. Okay, so there's the midpoint, half comma minus a half. Here's the point C that we saw earlier. And we want to map the circle K to the circle J. So what we do is we map the center of the circle K, which is the point with coordinates 3, 2. So we just follow this translation here to work out what the center of the new circle is. So if we look at the x values, we're going from a half to minus 2. That involves a subtraction of 2.5. A half minus 2.5 is minus 2. So we take 3 and subtract 2.5 to get a half. As for the y values of the translation, we have to add 2.5 onto minus a half to get plus 2. So over here we need to add 2.5 onto 2. Okay, that's going to give us 4.5, but 4.5 is the same as 9 halves. Now the radius of the image of circle K, that is the radius of circle J, is the same as the radius of circle K. And we saw that the radius of circle K is root 2. So now that we have the center and radius of circle J, we can get its equation using this formula that we derived earlier. So h is a half, k is 9 halves, r is root 2. Here the equation has been written in such a way that no fractions appear. So you do that by expanding everything out here, of course. You're going to get fractions involving a quarter. So you multiply everything by 4 to get rid of that denominator of 4. And also the right hand side has been brought over to have 0 on the right hand side. Now, obviously you don't have to do this. If you leave it in this form here, it's very clear what the center and radius is. The center is just got by changing the sign of this number from minus a half to plus a half, and changing the sign of this number from minus 9 halves to plus 9 halves. So that's the center, and the radius is just the square root of this number. You know, if you want to use the expanded form, which I've done here, just by expanding everything out, I've also put 0 on the right hand side. You know, you can just plug directly into this expanded form. H is a half, so you minus 2 halves or 1. Minus 2 times 9 halves is minus 9. You have to take h squared, add it to k squared, and subtract r squared. So that's a quarter plus 36 quarters minus r squared. R squared is 2. 2 is the same as 8 quarters. Sorry, this should be 81. If you work this out, you get 74 quarters. So now, if your equation is in this form, where the coefficients of x squared and y squared are both 1s, you can immediately note down what the center is by taking half the coefficient of x and changing the sign to get plus a half, and taking half the coefficient of y and changing the sign to get plus 9 halves. As for the radius, you can work it out from this number here. So just to see this again, this number here is c. C is equal to these numbers put together. That gives us the constant in the equation. The constant doesn't involve x or y. So from c equals h squared plus k squared minus r squared, we can rearrange to get r equals root h squared plus k squared minus c, the formula that we use for the radius. The glass square is of side L. We want to find the smallest number L such that the two cogs h and k are fully visible through the glass. So clearly we want the distance shown in red to be less than L. Well, the distance from here to the center of the circle is just the radius of this circle, which we saw earlier. It's 4 root. We also saw the radius of the smaller circle earlier. It's root 2. So finally we have to get the distance of D to F. F is a point directly below the center of this. Well, to find that distance, we just have to subtract the x coordinates. So we have 3 minus minus 2, which is 5. So we want 4 root 2 plus 5 plus root 2 to be less than the side of the square. So working all of this out, we get 12.07. So we want that distance to be less than L, but we also want L to be an integer. So, or a whole number, so we can see that L must be 13. Okay, I'll start by getting the center and radius of circle C2. Okay, we saw before the general equation of the circle in its expanded form. The coefficient of x is minus 2h, where h is the x coordinate of the center. So we have the coefficient of x and change the sign. So the x coordinate of the center is 1. To get the y coordinate of the center, you see that we have to half the coefficient of y, which is minus 2, to get minus 1, and change the sign to plus 1. Okay, because minus 2k is equal to minus 2. Now, c is the constant term. C is minus 7. We know that r is given by this here. So h is 1, k is 1, and c is minus 7. So we have minus c in the formula, minus minus 7. So we get root 9, which is 3. Okay, let's get the equation of circle C1. So, it's x minus h squared plus y minus k squared equals r squared. That's the unexpanded form. So the center is minus 3 minus 2, so h is minus 3, so we have x minus minus 3, x plus 3 squared, plus y minus minus 2 squared equals r squared. 2 squared is 4. So we could leave it in this form, or of course we could expand it out to get it into this other form. Now the line joining the centers of these two circles, as we know, passes through the point of contact of the two circles. And we want this point of contact of the two circles. Now you can use a formula for that, but if you don't know the formula, we can also work it out by considering these right angle triangles. Okay, so I've taken this smaller right angle triangle and shown it over here. Its hypotenuse is 2. As for the larger right angle triangle, the hypotenuse is 5. What about the other two sides? Well, we just subtract the coordinates to get the other two sides. So the vertical distance between the two centers is just 1 minus minus 2, which is 1 plus 2, which is 3. And the horizontal distance between the two centers is got by subtracting the x values. 1 minus minus 3 is 1 plus 3, which is 4. Now we have a pair of similar triangles here. Obviously the right angle is the same in both of them, and of course this angle here is common to both triangles. Okay, I can also show it here. So two angles are the same, so that means obviously the third angle is the same. Alright, so if that's the case, we know that corresponding sides are in the same ratio. So let's say that this here is y, and we want to find out what it is, because that will help us get the coordinates of this point here. Help us get the y value of that point. So we have to get this distance first of all. Well, we get the ratio of corresponding sides, so we look at these two. These are corresponding sides because they're opposite the same angle, this dot angle. So if we take that ratio, say 3 over y or y over 3, it doesn't matter. I'll write down 3 over y. Let's take another pair of corresponding sides. Okay, so let's look at this pair here. We want to find x, of course. So these are corresponding because they're both opposite this angle up here. So we have this side in the big triangle divided by its corresponding side in the small triangle is 4 divided by x. Well, actually we should really work with these two sides. Okay, so because we have both of these sides. Okay, so if we take the ratio of 5 to 2, it's the same as these two ratios. So now we can find either x or y. So, you know, we have 3 over y equals 5 over 2. So y is 6 divided by 5. Cross multiply, 5y equals 6. So y is 6/5. From 4x equals 2/5, if we do the cross multiplying with this here, we get 5x equals 8. So x equals 8 divided by 5. So now we can write down the coordinates. So we take the x coordinate of this point, which is -3, and add on to it 8/5. Okay, that's the distance from here to here. So we have -3 plus 8/5. And to find this distance here, well, we take the y coordinate -2 and we add on to it the value we got for y here, which is 6/5. Let's redo this problem using our formula. So we have the 2 points x1, y1 and x2, y2. So h begins at x1, y1. So that's important for this formula. So we want to divide our line, we want to pick a point, we want to find the coordinates of this point that divides the line in the ratio h is to k. Now we actually know what both of these lines are. This line here is the radius of one of the circles is 2 and the other one is 3. So if we know the actual lengths of both lines, well, the ratio is just got by taking h equal to 2 and k equal to 3. But of course h doesn't have to equal 2. H could equal something like 4, and in that case k would have to equal 6, as long as the ratio is 2 is to 3. So we could have 2 in for h, 3 in for k, or we could put 4 in for h, 6 in for k, and so on, as long as the ratio is 2/3. Okay, so we have h and k, and we have the coordinates of the endpoints. So just be careful here, we have to multiply h by x2, not by x1, and then we add on k times x1. So that's the x coordinate. The y coordinate looks exactly the same, except we replace x2 with y2 and x1 with y1. Yet another way to do this problem is to get the equation of the line joining the centres of the two circles. That's straightforward because we have those 2 points. And we get the equation of this tangent line here, which is common to both circles. It's a common tangent of both circles. Now we saw previously that the equation of a common tangent to both circles is got by subtracting the equations of both circles. Now, you know, to simplify things down considerably, we have to get the equations of both circles in expanded form. So let's look at this circle here, C1. So if we square this out, we get an x squared here, we get a y squared here. I'll just write it in the standard expanded form. We have a 6x from this square. From this square here we have a 4y. As for the constants, we have a 9 here and a 4 here, that's 13. Subtract the 4 and we get 9, so we're left with 0 on the right hand side. So that's the equation of C1. So we take that equation and subtract C2 from it. Okay, so from the left hand side of C1 we subtract all of this thing here, and square terms disappear. So we have 6x minus 2x, that's 8x. We have 4y minus 2y, that's 6y, and we have 9 plus 7, that's 16. And that's we've taken all of this thing here from the left hand side of C1. Next we take 0 from the right hand side of C1. So you see we're taking the same thing from both sides of C1. So we get a true equation. If we take 0 from 0, we get 0. But notice we get the equation of a line. So we saw before that the point or points of intersection of the two circles actually lie on this line. Only the points of intersection lie on this line. So this thing here must be the equation of the common tangent of both circles. So you can see it's a very simple calculation. By subtracting the circles, we get rid of the square terms. We're left with a linear equation. You know, x to the 1, y to the 1. So we must get the equation of a line. Only the points of intersection of both circles satisfy both equations simultaneously. So that means that if we do the subtraction, those points of intersection will satisfy this here. Only the point or points of intersection will satisfy this. Now there's only one point of intersection here. So we need to solve between this line and, as I said earlier, the equation of the line joining the centres of the two circles. So I won't do that. But of course if you do all that, you'll get this result here.